So this video is going to take you through as quickly as possible Unit 2.9 Gas Chemistry. It's not the most exciting topic, I have to say, and it's pretty straightforward, so I'm hoping that you can work through most of it independently. If you have a brief look at the specification, you can see that the first section is about the composition of gases in the atmosphere, which we'll look at shortly. Then essentially you look at nitrogen, first of all, as your first gas. And then if you turn over the page, the next gas you look at is hydrogen, and we look at how we prepare it and its physical properties, its uses, and so on. Then we move on to the gas oxygen, and again we look at its preparation, its properties, its uses, and then have a look at some reactions of oxygen as well. And then next we move on to our final gas, carbon dioxide. We look at its preparation, its uses, its properties, and some of its reactions as well. This topic also contains your sixth and final prescribed practical, looking at preparation, tests and reactions of these gases, hydrogen, oxygen and carbon dioxide. So this could come up in your practical exam and also your practical theory exam. So you need to know these gases well and their preparations, tests and reactions. So turn over to page 3 in your booklet and you'll see a pie chart of the composition of gases in the atmosphere. You need to know these percentages. You need to know the percentage of each gas. And quite often it comes up on exams as perhaps a little table that you have to fill in the missing percentages. You could colour this pie chart in if you wish, or it is slightly coded, but some of them look quite similar. So the main gas in the air is actually nitrogen. Sometimes we think that it's mostly oxygen, but in fact it has a higher percent of nitrogen. Nitrogen is a very unreactive gas, as we'll see. We don't need it as such for respiration or anything like that, but because it's such an unreactive gas, we essentially breathe it in and breathe it out. If you look at the comparison of the percentage of air that we breathe in and air that we breathe out, the air that we breathe in is 78% nitrogen, and the air we breathe out is 78% nitrogen. That means our body doesn't use it or doesn't make it during respiration. So it's 78% nitrogen, 21% oxygen, 0.03 to 0.04 carbon dioxide. So learn that number carefully, it's a little bit more difficult. But also you'll see that varies from 0.03 to 0.04. Think of a few reasons why that is. Things like depends how much fossil fuels you're burning, how many plants you have in a certain area that will be removing carbon dioxide from the atmosphere in photosynthesis. So that level of carbon dioxide will depend from country to country and area to area, and also at particular times of the day. Carbon dioxide levels can be higher or lower, they can fluctuate, or at a particular time where maybe factories are working more, etc. So that percentage can vary. The next percentage you have to learn is that it's 1% argon. So 1% argon, it's one of your noble gases. And then the remainder of the noble gases, they make up a small proportion. You just need to learn a small proportion. And then water vapour, you need to learn it as varying proportions. Again, depends on your country, where you live, weather conditions and so on, humidity, etc. What percentage water vapour makes up. So that's varying proportions. So the first four are the key ones that you have to actually learn specific percentages. And then know that noble gases make up a small proportion and water vapour makes up varying proportions. Next on page 3 looks at a summary of the gas tests in this topic. You'll remember that our 4 key gases are nitrogen, hydrogen, oxygen and carbon dioxide. There's no test for nitrogen as such because it's so unreactive. But you do need to know these gas tests well, which is why they are summarised here. When we look at each one of these gases in turn, we'll come back to this. But you need to know these really well. These tend to be 2-mark questions. If you were asked, how do you test to see if a gas is hydrogen? You would not get the marks for just saying the squeaky pop test. You haven't actually said how you have done it. And you haven't said what actually specifically happens. So if we take a look at hydrogen here, first of all. So if they said, how would you test a gas to see if it was hydrogen? You would say, apply a lighted splint or a lit splint, and a popping sound will result. So this would be your first mark. This would be your second mark. Same again for oxygen. How do we test for oxygen? Well, instead of applying a lit splint, we apply a glowing splint. What we mean by that is a splint that we have lit and is burning, but then we've blown it out, but it is still glowing around the edges. And if you put that into a test tube or a gas jar of oxygen, the splint will fully relight. So again, the first mark is for saying apply a glowing splint. Second mark for saying the splint will relight. And then finally, the test for carbon dioxide. Again, your first mark will be for saying pass the gas through lime water. Second mark for saying, well, what is the change that happens? And that is that the lime water will change from colourless to milky. So it's a little bit different. You have to bubble the carbon dioxide through lime water, and that lime water changes from colourless to milky. So all of these tests you've seen before, but you have to learn them, and you have to learn them in a specific way of how to quote them. And if you look through your past papers, you should find a 6-mark question on this, in fact. And the 6-mark question basically said a student has 3 gas jars. One contains, I think it was nitrogen, oxygen and carbon dioxide. How would you test each gas within the jars to determine which was nitrogen, oxygen and carbon dioxide? So actually they could turn this gas test part of the topic into a 6-mark question. So what you would be saying, you can do this by a process of elimination. You would be saying you could test all 3 gases to see if they were oxygen by applying a glowing splint to each gas jar. If the splint relights, that gas is oxygen. So then you would be down, you'd have ruled out which one's oxygen, then you would be down to 2 gas jars. So you would test the next 2 for carbon dioxide. So you would bubble some of each gas through carbon dioxide. If it turns lime water from colourless to milky, then that one will be carbon dioxide. That shows which one's carbon dioxide. And then the remaining gas jar will be nitrogen. As you can see, we don't have a test for nitrogen, but in this sense, you were doing it by a process of elimination. Test each for oxygen. I'm describing how you do that. Test the remaining 2 for carbon dioxide and explain how you do that. And then the final one will be nitrogen, explained by a process of elimination. So that's your gas test. Make sure you know them really well. What we're going to do now is we're going to look at each of our gases in turn, and after we have looked at each gas, I want you to fill in your mind map for each of the gases. You have one for nitrogen, hydrogen, oxygen and carbon dioxide. So once you've done nitrogen, pause the video and fill in your mind map. Nitrogen won't take us very long. It's a very unreactive gas, as we've already said, and so therefore it's not too exciting and we don't have too much to learn with it. With nitrogen, I have given you the link to a YouTube video, a periodic table video on nitrogen. It's only the first few minutes that are relevant, but you can watch on if you like to have a look at some gases of nitrogen, like nitrogen oxide and so on, but it's the first few minutes that are relevant if you want to have a watch at that. So as we know, nitrogen is the most abundant element in the Earth's atmosphere. Have a think, what percentage did it make up? It made up 78% of the Earth's atmosphere. Nitrogen has the formula N2, which means it exists as a diatomic molecule. And sometimes it has come up on past papers, what is the definition of the word diatomic? And that relates to this topic. And all it means is di means 2 and atomic obviously means atom. So it essentially means two atoms that are covalently bonded together. That brings us back to last year. Covalent bonding is the sharing of electrons between two non-metal atoms. So if we have a look at what our diatomic molecule would look like in terms of its bonding, you probably wouldn't be asked this year, and this was more from year 11, but they could bring it back as all previously learnt knowledge. So nitrogen actually has a triple bond in it, and we represent that by drawing 3 pairs of electrons in the overlap. And each nitrogen atom will also have a lone pair. So if you think about nitrogen, it's in group 5 in the periodic table, which means that it has 5 electrons in its outer shell. You can do the full version, it has 7 electrons, but 2 electrons would go in the first shell, 5 in the second shell. So it has 5 electrons in its outer shell. That means essentially each nitrogen atom is sharing each one of its single electrons. It's sharing that with the other nitrogen atom. So that's your diatomic molecule diagram. So fill that into your notes. So the 3 shared pairs of electrons in your overlap indicate that nitrogen has a triple bond, a triple covalent bond. Sometimes we represent that as N, triple bond N. And actually that determines a lot of nitrogen's chemical properties. The fact that it's held together by a triple covalent bond makes it very unreactive, and we'll come back to that in a second. For each gas, you need to know the physical properties. Some of these are the same for each gas. And with nitrogen, we see that it's a colourless, odourless gas. There's a wee S missing in there, and there should be 2 S's at the end of odourless. But again, you might see this as a lot to learn, but think about the air around you. It's colourless and it's odourless, and it's made up of 78% nitrogen. So that reminds us that nitrogen is a colourless, odourless gas. So just think about the air around you. So it's a colourless, odourless gas. It's insoluble in water. What does the word insoluble mean? It just means that it doesn't dissolve in water. So if we bubbled nitrogen through water, it would not actually dissolve into it. And it's a neutral gas. In other words, it's not acidic, it's not alkaline. So it's a neutral gas. So you need to know those 4 physical properties. Okay, now we're looking at the reactions of nitrogen, and as we've said a few times, nitrogen is very unreactive because it has this strong triple covalent bond. If you look back up at your covalent bonding diagram, and this representation here. So the fact that it has a strong triple covalent bond means that when we try to react it, that triple covalent bond would have to break first of all before the nitrogen atoms can react with anything else. And that's going to take a lot of energy to break that bond. So when you're asked to explain why is nitrogen so unreactive, what you would be saying is that the atoms are held together by a strong triple covalent bond, and a lot of energy is needed to break this bond before the nitrogen atoms can react. So that's almost a 2-mark explanation. And you will need to come back to that in your mind map when you're summarising nitrogen. Why is it unreactive? Because the nitrogen atoms are held together by a strong triple covalent bond, and so a lot of energy is needed to break this bond before the nitrogen atoms can react. And then finally, let's look at some uses of nitrogen. You do need to know these in a bit of detail, but when you're learning it, just learn these key phrases. So I would be learning for nitrogen coolant, food packaging, and manufacture of ammonia, as simple as that. Let's explain these in a little bit of detail. And again, you'll see these referred to in the periodic table video that I have linked you to in the separate Word document. So liquid nitrogen, first of all, is used as a coolant in refrigerated lorries and in computers. This is actually due to one of the physical properties of nitrogen, that it has a boiling point of -196 degrees Celsius, and that means that if I want it to become a liquid, I have to cool it down to lower than minus 196 degrees C. So liquid nitrogen is very, very cold, and we have to keep it at that temperature to keep it as a liquid as such, and so it can be used to cool other things then. So we use it as a coolant in refrigerated lorries, and to freeze food products and stem cells. It's used as food packaging as well, and that is because it is so unreactive. So if you think of a packet of crisps, you know, the packet of crisps pop when you open them, or you know that they're full of a gas. That gas is actually nitrogen. It's not air, because if it was air, then our crisps would go soggy. You know that if you leave a bowl of crisps sitting out, that it will go soggy even overnight, and they'll not quite be as crispy. So crisp packets are pumped full of nitrogen, and that makes sure the crisps stay nice and fresh, and don't go off, don't go soggy, and that's because nitrogen is so unreactive. That word inert just means unreactive, so it's providing an inert atmosphere to keep food fresh, and it's safe and unreactive. Then finally, nitrogen is used in the manufacture of ammonia. It actually reacts with hydrogen in a reversible reaction. You may have seen this back in our equilibrium topic, to form ammonia, which has the formula NH3. That's the balance symbol equation for it. But that's where nitrogen is used in the manufacture of ammonia. And ammonia is commonly used in fertilizers, so it's really important. So I would learn with that one that it's used to manufacture ammonia, and that's used in fertilizers. So that's nitrogen finished. You just basically need to know its properties, the fact that it's unreactive, and a few uses. So what I'd like you to do now is to get your nitrogen mind map out. I'm going to show you that now. So here's your nitrogen mind map. I want you to get this out and complete it. It shouldn't take you too long. So in the space here, if you write nitrogen, it's N2, and you could even draw your diatomic molecule in the bonding diagram with your 3 pairs of electrons. I know mine are quite small there, hard to see. 3 pairs of electrons in the overlap, and 1 pair in the outer shell, and 1 lone pair for each atom. You could draw that in there as well. So it's 3 uses, it's 4 properties, and explaining why it is so unreactive. Use your notes on the previous page that we were looking at there to fill that out. It should take you no time at all. So pause the video, do that now, before we then move on to hydrogen. So the next gas that we're going to look at is hydrogen. And again, it's a diatomic molecule. If you think of where hydrogen is in the periodic table, it's our first element, which means that it only has 1 electron. And that's obviously in its outer shell. So with hydrogen, what it does is it shares these electrons that it has, the single electrons in the outer shell, to become a diatomic molecule. And what we end up with is a diatomic molecule with 1 electron from each hydrogen atom in the overlap. That means that hydrogen simply has a single bond in it, because there is only 1 pair of electrons in the overlap. In other words, 1 shared pair of electrons, which is a single covalent bond. So it's going to be more reactive than nitrogen in that we only have a single bond rather than a triple bond. Again, the physical properties of hydrogen. Well, if you think you have prepared hydrogen before when you were reacting metals with acid, for example, we know that again it's a colourless, odourless gas. So that's common with nitrogen as well. It's less dense than air, and we know that from our reaction of metals with acid as well. So if you think if we were to react a metal with acid, so if we have a test tube of, let's say, hydrochloric acid here, and we were to add a strip of magnesium, the gas formed would be hydrogen. And if you think back to when we did this in our reactivity series topic, we would have collected the hydrogen by simply putting a boiling tube on top of that other boiling tube where our reaction is happening. And that means that our gas is passing into the boiling tube. It's less dense than air, so it's rising up and it's collecting in this top boiling tube. So we've seen that before, it's less dense than air. It's insoluble in water, which means if we pass it through water, it won't actually dissolve in the water, so it doesn't dissolve in water. And again, that is common to nitrogen as well. It burns explosively in air. So again, think of the pop test here. Think of your test for hydrogen. When you apply a lit splint to hydrogen, you get a squeaky pop, which is actually an explosion. We'll come back to that in a second. So it burns explosively in air and it is neutral. Again, it's not acidic or alkaline. We've talked about this already. The test for hydrogen is that, first of all, what do you do to test for hydrogen? Well, you apply a lit splint to the gas. And then what happens if it's hydrogen? So think, what do you do? What happens if it's hydrogen? So first of all, what do you do? Apply a lit splint. What happens if it's hydrogen? A popping sound will result if the gas is hydrogen. And the reaction happening is actually hydrogen reacting with oxygen. So if you apply a lit splint to something, you're trying to burn it, and burning is the reaction with oxygen. So when hydrogen reacts with oxygen, we get water, and the balance symbol equation for that is given to you there. So hydrogen gas reacting with oxygen gas to give water, which is a liquid, and that's what your little state symbols mean there. So the preparation of hydrogen in the lab is done by simply reacting any metal with any acid, because we know the general equation for that is metal plus acid gives us salt plus hydrogen. That's something we learnt last year in Unit 1.8, acids, bases and salts. You may have learnt it as MASH, metal plus acid gives salt plus hydrogen. So think of that general reaction you already know, and that's how we make hydrogen. One of the products of that reaction is hydrogen. You may have seen me do this in class, or you may have seen me do something similar in preparing oxygen in our rates of reaction topic. But specifically, you need to learn it as the reaction of hydrochloric acid with zinc or magnesium. So the reaction of dilute hydrochloric acid with zinc or magnesium. The reason why that is because if we were to use concentrated acid, it would be too reactive. And similarly, if we were to use a metal like calcium or sodium or potassium, again, the reaction would be far too vigorous for us to collect hydrogen safely. So this is essentially to ensure a controlled reaction. So you may get asked that in an exam. Why is sodium not used in the lab to prepare hydrogen? And that's because it's too reactive. The reaction would be too vigorous. So we use zinc or magnesium instead to ensure a controlled reaction. So again, think back to your properties of hydrogen. We said that it was insoluble in water. And what that means is that we can collect the hydrogen produced over water. So that's a key phrase to highlight as well. If you were asked, how is hydrogen collected? And it was only a 1 mark question, you would simply say it's collected over water. And you're going to have to put that into your mind map as well. So highlight that. How is it collected? And it's over water. And that's because you can see that when you pass it into water, it will not dissolve in it. So have a look at the apparatus here. This is apparatus that you need to learn. It's apparatus that you could be asked to draw or could be asked to complete, or quite often it's been given to you but you have to label the different pieces of apparatus. So what we've got is the reaction happening in this conical flask. So basically this thistle funnel here, quite often it would have like a little tap where you can control what you're adding in. This would be for adding in liquids or solutions such as your hydrochloric acid in this reaction. So you would have your zinc already sitting at the bottom of your conical flask. And what you would do is use the thistle funnel to add your hydrochloric acid, and then you would close the tap to make sure any of the gas didn't escape up through that piece of glassware. Then what will happen is the zinc will start to react with the hydrochloric acid. You'll get a gas produced, and that's going to go through your delivery tube and into the gas jar here. This thing here called a beehive shelf is just like literally like a little shelf with a hole here to allow the delivery tube to pass in. It'll also have a hole here so that the gas can then move up into the gas jar. So the gas jar is literally just sitting upside down on top of it. That's all full of water. And the hydrogen, because it is less dense than air and because it's not going to dissolve in the water, it floats up to the top and it actually displaces the water. So because it's not dissolving in the water, it's displacing the water. The water level is going to go down, and this is going to eventually completely fill with hydrogen. So water level's going down, it's flowing through here, and eventually it'll kind of come up in this trough of water. The level of water of your trough will eventually rise up here. You don't need to add any of that in, but just explaining where does that water go. It'll go out from the gas jar through the beehive shelf and back into the trough again. So you will see that water level start to rise. So your gas jar will fill with hydrogen, and then you can just collect multiple gas jars of hydrogen, and you can test that gas to see if it's hydrogen by using your test for hydrogen by applying a lit splint, and a popping sound should result. So be familiar with that apparatus. Make sure you're able to label that apparatus. And the equation here, we've gone particularly for zinc plus hydrochloric acid. Pause the video now and see if you can write a balance symbol equation for this. If you're not so sure at this stage, then you can watch along with the video, but you need to be able to write these types of balance symbol equations. So give it a go yourself first of all. Hydrochloric acid is HCl if you need that. So pause the video, give this a go, and then I'll go through it. So again, remember when you're writing a balance symbol equation, you're simply converting each reactant and product to its formula first of all. So the formula for zinc is Zn. Then I put my plus symbol in to separate it from my next reactant, which is hydrochloric acid, which is HCl. Put your arrow in, just as with your word equation. Then zinc chloride I need to have a think about. So zinc, it's a transition metal. You're not given its valency here, and it doesn't have a group number. So check the back of your periodic table, if you have your periodic table out. If not, pause the video, get it out so that you can see this. On the back of your periodic table, you should see that zinc has a charge of 2+, which means its valency is 2. Chloride then is simply chlorine. It's not diatomic because it's part of a formula, it's part of a compound now. And so we look to the top of its group to get its valency. It's in group 7, so has a valency of 1. When we swap and drop, we get a formula of ZnCl2 plus hydrogen. And we remember that hydrogen is a diatomic gas, so we must write it as H2. So that's your symbol equation written, but it's not balanced at this stage. And so what you need to do is to balance it. You can make your list if you're not too confident at this stage. But looking at this equation quickly, we can see we have 1 zinc on either side. But the problem is with our hydrogen and chlorine. We have 1 hydrogen and 1 chlorine on the left, but we have 2 chlorines and 2 hydrogens on the right. So I can fix this. Remember, when balancing an equation, you can only put numbers in front of a formula. So I can put a big 2 in front of my HCl. That now gives me 2 hydrogens, 2 chlorines, and so my equation is balanced. Down below you just have some observations of this reaction, that during this reaction, and essentially what we're talking about is what's happening in the conical flask. We're going to get bubbles of colourless gas. You could refer to that as fizzing. Well, what is your colourless gas? It is hydrogen. The zinc metal will eventually disappear, or magnesium if you're using that. You form a colourless solution that will be of essentially your solution of zinc chloride, your salt that you formed, and heat is released in this reaction as well. So this is a reaction that you've done plenty of times before throughout your time in science, right from junior school and even in our reactivity series topic. So reacting zinc with acid will produce all of these observations. And the key thing is that during this reaction, you produce hydrogen gas. We can see that in our equation. And collecting that is a way of preparing hydrogen in the lab. And remember that the collection is over water because it's insoluble in water. And then finally in this topic, we have to simply look at its hydrogen's uses. So again, you need to know a bit of detail about this, but again, briefly learning these, try and minimise it down to as much as you can. Hydrogen is used to harden oils in meteorological balloons, in other words, weather balloons. And it has a potential use as a clean fuel, which we'll come back to in a second. So first of all, hardening of oils. This is something that is studied further at A level, and we'll mention it briefly in our last topic of organic chemistry. But essentially, vegetable oils like olive oils contain carbon-carbon double bonds. So these carbon-carbon double bonds. And that causes oils to be liquids at room temperature. So say for example, and we'll come back to this in our organic chemistry topic, say for example we had a molecule containing these carbon-carbon double bonds. So it would look something like this, okay, within a chain. If we were to add hydrogen across that carbon-carbon double bond, the carbon double bond would break, leaving just a single bond. And the hydrogen would add across that. So if I change the colour of the hydrogen, you can see that. So the two hydrogen atoms would essentially split off from each other, and one would add to each carbon atom. And what you can see is that you're just left with a single bond between your carbon atoms instead of a double bond. And that actually increases the melting point of our vegetable oils. And that causes them to become harder, in other words, makes them more solid. And that's actually how margarine is made from your vegetable oils, is that it undergoes a hydrogenation reaction where hydrogen is added across those double bonds within the chain, makes them more solid and makes solid oils like margarine. So then also hydrogen is used in weather balloons, and it also has a potential use as a clean fuel. You do have to look at the advantages and the disadvantages of hydrogen as a fuel. So if we take a really quick look at what a fuel cell is, you don't need to know too much of the detail of it, but essentially it is using electrochemistry, which we've studied before now, and within this, the fuel cell produces electricity. And hydrogen is simply reacting with oxygen, and the only byproduct is water, and that's why it has the potential to be used as a clean fuel. So we know that when hydrogen reacts with oxygen, we get water. To balance that equation, you need a 2 here and a 2 here, and that's why it has the potential to be used as a clean fuel, because the only product is water, which we know is non-pollutant, whereas if you think of fuels that contain carbon, they're reacting with oxygen to produce carbon dioxide, which we know is a greenhouse gas and can lead to the greenhouse effect and in turn global warming, whereas hydrogen is a clean fuel. It only produces water, which is a non-pollutant. That's a simple diagram of a fuel cell. You don't need to know the ins and outs of it, but know that in this process, hydrogen and oxygen react together to give water, and electricity is produced as a result. So that is all summarised here, where you've got the advantages of hydrogen as a fuel. So you can see that fossil fuels, they tend to be burned in cars and vehicles and in our homes, but when they burn, they release harmful gases that can contribute to the greenhouse effect. And that's mentioned here. And also because the supply of fossil fuels is running out, then scientists are looking at alternative fuels because fossil fuels are non-renewable and their reserves are low. And with hydrogen we can generate it renewably, and we'll come back to that in a second. So first of all, an advantage of it is that the only product of the reaction of hydrogen with oxygen when we burn hydrogen is water, which is a non-pollutant. So the only product is water, which is a non-pollutant and doesn't add to global warming. And can also be used safely in fuel cells, where hydrogen is converted to water only. And fuel cells are starting to be used to power some vehicles. And finally then, in terms of its advantages, it can be produced from the electrolysis of water. So the hydrogen itself can be produced from the electrolysis of water, which is essentially the reverse reaction of hydrogen burning with oxygen. So the electrolysis of water will be water splitting up into its elements, hydrogen and oxygen. And we'll just balance that equation there, to be precise. And obviously water is renewable, so this source of hydrogen can be renewable. And if we generate the electricity for the electrolysis of water from renewable sources of energy like tidal, solar, wave, hydroelectric, that helps preserve our fossil fuels and also increases the potential of hydrogen as a clean fuel. So electrolysis, as we know from our electrochemistry topic, can be very expensive, and it can use up fossil fuels if we're using that to generate our electricity for it. But what we're saying is that if we generate the electricity from renewable sources like tidal, solar, wave, hydroelectric, that increases the potential of hydrogen as a clean fuel, because you're not using fossil fuels, you're using renewable sources of energy to get your electricity and to split up your water to provide the hydrogen for the fuel cells. However, it's not a perfect solution. Hydrogen is not a perfect fuel, and you do need to know the disadvantages. And technically speaking, this could be a 6-mark question weighing up the advantages and disadvantages of the use of hydrogen as a fuel cell. So in terms of using hydrogen in a fuel cell, it would have to be supplied in a liquid form. And keeping hydrogen in a liquid form requires a lot of energy and specialised storage and transport. So that can be very, very expensive. So if you think of the likes of liquid nitrogen, the temperatures that it had to get to keep it as a liquid form, you're going to have really high pressures and so on, and that's going to require specialised storage to make sure that it's safe. And that brings us on to the second disadvantage. First of all, we know that hydrogen is very flammable and explosive. Think of your pop test, that the kind of explosion, small scale explosion that happens even on like a test tube scale. So if you're transporting large amounts of hydrogen, that's going to be very dangerous and high risk. So you're going to have high levels of control and people who are specialised in transporting and dealing with that hydrogen. And fuel cells are also very expensive to build. The fuel cells themselves, which operate this reaction of hydrogen with oxygen to produce electricity, are very expensive to produce. And also how we get our hydrogen. We discussed in the previous page of renewable ways of sourcing the hydrogen through the electrolysis of water. But more common ways of producing hydrogen is from burning methane, which is a fossil fuel, and that releases carbon dioxide in the process, which is a greenhouse gas, which will contribute to the greenhouse effect and global warming. And even if we're using electrolysis, if we use fossil fuels to generate the electricity, that's going to give off carbon dioxide as well, a greenhouse gas. So that's why we said in the previous page, if you're preparing it by electrolysis, try to use renewable sources of electricity such as tidal, hydroelectric, and so on. So there you have the advantages and the disadvantages of hydrogen as a fuel. And you must know the advantages and disadvantages of it and be able to weigh that up. So again, what I want you to do is complete your mind map for the hydrogen section of this topic. I'll show you that now. So here is your mind map. You can see it's a little bit more detailed than nitrogen because you have a lot more going on here. So again, write in your formula for hydrogen, it's H2. And if you can fit in, do your little bonding diagram there. My circles aren't great, but you can make yours a bit neater. So that you can see it's a diatomic gas. So again, in this case you need to do your properties, your test for hydrogen, your preparation of hydrogen, and remember your collection is that phrase over water. Okay, for the equation you can write a word equation or a balance symbol equation, whatever you can fit in, or whatever you can will help you learn this. Your reactants are the things you react together. So what do you react together to give you hydrogen in that preparation? So go back to your notes for that. What are you reacting together to give hydrogen? It's uses, just a summary of the uses, and then a summary of the advantages of hydrogen as a fuel and disadvantages of hydrogen as a fuel. So complete that now before you move on to the next gas, which is oxygen.